Welcome back, Pre-Calc Excel students. In this lesson, we are going to begin Chapter 12 with your introduction to limits. We discussed limits briefly in the past, so let's go through the definition again. The definition of a limit is if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L. So what that's saying is if we have a function and those function values are approaching a number, okay, we choose an x value, which is c, and on either side of c, if our function values are approaching that same number, then that number L is our limit, the limit of the function at that particular x value or as we approach that x value. So first we're going to look at how to estimate a limit numerically. And we're going to use a table. I started off with something that you can identify with, right? 5x minus 3, we all know that's a line. And as x approaches 3, we're going to look at the values on either side of 3. So the values from the left, as we get closer and closer to 3, we have 2.9, 2.99, and so on. And you can see what those y values are approaching. When we approach the number 3 from the right-hand side, we have 3.1, 3.01. We're getting closer and closer to 3. And in both cases, as you can see, the graph, the function values are approaching that same value of 12. And you'll see later we'll talk about the direct substitution technique, which we can actually plug the 3 into this function and get 15 minus 3, which is 12. But this is a good technique for when we can't do direct substitution. I just wanted to start off with, again, a graph that you can relate to, a function that you can relate to, and see where that value of 12 is coming from. So let's try another one. Here we have the limit as x approaches 0 of x over the square root of x plus 9 minus 3, and that minus 3 is outside the radical. So here, as you can see, if we did a direct substitution, we would get 0 over 0, which is considered to be indeterminate. So we can't do direct substitution here. So a technique like a chart or table is a good one. If we look on either side of 0, here I'm choosing values from the left-hand side. As we get closer and closer to 0, you can see what the y value is approaching. Okay, looks like 6. Let's check it from the right-hand side. As we get closer and closer to 0 again, our y values are getting closer and closer to 6. So the limit as x approaches 0 of this function is equal to 6. And that last one, I didn't put it here, but this limit would be equal to 12. Okay, so this is an example where the existence or non-existence of f of x at x equal to c has no bearing on the existence of the limit. So what that's saying is that even though we can't calculate f of 0, we can calculate the limit as x approaches 0. Here's another example. Again, if we were to plug in 3, we would get an indeterminate. So if I look at the table as I'm approaching 3 from the left, there's our y value. And as we approach 3 from the right, okay, so here's from the left, and here's from the right. Okay, as we get closer and closer, we can see that from both sides, we're approaching that y value of 7. Now, if you remember back when we talked about rational functions, we could actually do the graph of this by reducing out the common factor of x minus 3, and we end up with a quadratic. Here's the graph of that quadratic, and remember when you have that common factor, do you remember what happens? That means that instead of a vertical asymptote, we have a hole in the graph at 3. Okay, but on either side of that hole, the y values are approaching 7. So again, even though we cannot calculate f of 3, we can calculate the limit as x approaches 3, and that limit in this case is 7. And 3, 7, the point I put here, that's where the hole is located in the graph. So we're looking at some odd cases. You'll see most of what you will work with in calculus is continuous functions. So right now we're looking at a lot of the oddball cases. So here's a piecewise function. We have f of x equal to 1 when x is not equal to 5. And then f of x is equal to -2 at x equal to 5. So that gives us this graph. We have the horizontal line, y equal to 1. We've got a hole where at x equal to 5. And then we have the point 5, -2. So the limit of this piecewise function as x approaches 5, what do you think it would be equal to? This would be a good test if you're following what I've been explaining, which I hope I've done well, but or what you want to look at is what's happening as we approach that value, x value of 5 from the left, and as we approach it from the right. So if you said -2, unfortunately that's not correct. The values, the y values, as we get closer and closer to x equal to 5 are approaching 1. So the limit of this piecewise function is 1, not -2. So this tells us that the limit of f of x as x approaches c is not equal to f of c. And again, we're talking about strange cases here. You know, when you have a continuous function, like the very first one we talked about, that was the line, you wouldn't have something like this. But right now we're looking at discontinuous functions where there's gaps, okay, in the graph. Okay, limits that fail to exist. So here, let's see, we have the function x over the absolute value of x, and we're looking at the limit as x approaches 0, which this is another important thing to bring up too. Okay, in a lot of these cases that we've talked about just now, I could calculate the limit as x approaches other values, like here, as x approaches 0, right, without any issues because the graph is continuous there. So keep that in mind as well. Because when we're talking about limits that fail to exist, it only fails to exist as x is approaching 0 for this particular graph. If I asked you for the limit as x was approaching 5, you would say 1, because on either side of x equal to 5, the y values are approaching 1. When we look at x as x, when x equals 0, the y values from the left-hand side are approaching -1, and the y values on the right-hand side are +1. So the limit as x equals, or as x approaches 0 of x over absolute value of x is, it fails to exist. So we put DNE for does not exist. And you're going to follow that up with the reason. In this case, the reason is different left-right behavior. Okay, so we could say, I'm going to show you the notation for one-sided limit, which I think you have seen before. So the limit as x approaches 0, as x approaches 0 of x over absolute value of x, as it approaches 0 from the left, is equal to -1. And the limit as x approaches 0 from the right of x over absolute value of x is equal to +1. So we can say, therefore, the limit as x approaches 0 of x over absolute value of x does not exist. So that would be the formal way of how to explain why the limit does not exist. But as long as you say does not exist because of different left-right hand behavior, that's fine. I'm just showing you a little bit of notation. So this is showing that the left and right hand limits are different. And if they're different, then the limit as x approaches that value, which in this case is 0, does not exist. That's what it's all about. Okay, when we look at the graph of 1 over x to the 4th, as x approaches 0, from the left, our y values are getting larger and larger. And the same thing from the right, they're getting larger and larger, right? Approaching infinity. So remember, we defined the limit as a number. Okay? Later it will be redefined, but for now, we're defining it as a number. So if it's a number, and our y values are approaching infinity, infinity is not a number. So here again, this limit does not exist. And the reason for this one is because the graph is unbounded. So we can just say does not exist, unbounded. Okay, the sign of 1 over x. If you look at this on your calculator, it's really hard to get a good picture of it unless you really zoom in. But what's happening here is our values as we approach 0 are ping-ponging back and forth between -1 and 1. Okay, so as I keep choosing the value closer and closer to 0, it's not the same, right? It's going back and forth and back and forth and back and forth. So this limit also does not exist. And the reason for this is because the graph is oscillating. So those are our 3 reasons of why the graph would not exist, or I'm sorry, why the limit would not exist. Okay, so your choices are either different left-right behavior, or that the graph is unbounded, the y values, again, approaching infinity or negative infinity, or the third possibility is that the graph is oscillating, like this one does. So those are your 3 reasons for why a limit would not exist. Okay, so the introduction to the properties, we might as well run through these, even though it says day 2. I'm going to give you the whole video today. So our basic limits, we have b and c, which means this means element of the reals. N is an element of the positive integers. So we have the limit of b. Okay, so b is some real number as x approaches c. So for instance, think of it as if b were 2, right? The function 2, that's just a horizontal line. So as x approaches c, doesn't matter what c is, that value is going to be b. The limit of x as x approaches c. Now here again, think of this as y equal to x or f of x equal to x. It's that line that goes through the first and third quadrants. Okay, so if we check the limit as x approaches c, it's going to be c. Okay, so for instance, let's say x or c is the value of 3, right? As x approaches 3, okay, the y value is also approaching 3. Okay, the limit of x to the n as x approaches c. So again, c could be any value. So this would just be c to the n. Okay. The limit of the nth root of x as x approaches c would just be the nth root of c. And that's if n is even and c is greater than 0, of course. We can only take the even root of a positive value. The properties, again, same restrictions here. B and C are elements of the reals, and n is an element of the positive integers. So we're setting the limit of f of x as x approaches c equal to L, and the limit of g of x as x approaches c equal to k. So if we have scalar multiplication, if we were taking the limit as x approaches c of b times f of x, that would be the same as b times L. So again, the properties just give you different ways of working with the limits. Okay, so we can take the limit of f of x and then multiply b times that, rather than doing b times the function. For sum or difference, the limit as x approaches c of f of x plus or minus g of x, we can separate this into the sum or difference of the two limits. So it's equal to L plus or minus k. So if it's easier to take the limit of each function and then add or subtract, you can do that rather than adding or subtracting the functions first. If it's the limit of a product, again, we can do the limit of each and then multiply. So this would be L times k. Same thing for the quotient. If it's easier to calculate the limits and then divide, we can do L over k. And then finally with the power, we take the limit of the function, we can then take that limit and then raise to the power, all to the n. So let's look at, let's see, for polynomial and rational functions. So if p of x is a polynomial function and c is an element of R, element of the reals, then the limit of p of x as x approaches c is equal to p of c. And this is going back to the direct substitution that I was talking about. If we have a polynomial function, remember that's a continuous function. We don't have to worry about any discontinuity. So we can do that direct substitution and calculate the limit as p of c, substituting c in. If it's a rational function given by p of x over q of x, and c is an element of the reals, such that q of c does not equal 0, then the limit of r of x is equal to r of c, which is equal to p of c over q of c. So again, that's as long as q of c does not equal 0. In our earlier cases, it did, right? So that's why we couldn't do the direct substitution method. So finding limits by using direct substitution and properties of limits. So here, just to show you, I'm going to show you, this is an easy direct substitution. We know the graph of x cubed is continuous, so I can just calculate this as 2 cubed. Okay, and that's equal to 8. Now, to use the property, if you wanted to take the limit of x as x approaches 2, okay, and then cube that, the limit of x as x approaches 2 is 2, and 2 cubed again is 8. So that's how you could use that power property if you wanted to. Here 8x, we know that's a line. There's no issues with discontinuity. We can do direct substitution and plug in the 4, and we would get 8 times 4, which is 32. Okay, if you wanted to separate this into a product and do the limit of 8, I don't think anybody would really want to do this, but I just want to show you that it is an option. Times the limit of x as x approaches 4. Again, the limit of a constant is just that constant. The limit of x as x approaches 4 is 4. And again, that gives us 8 times 4. Fourth root of x. Okay, do you remember what the fourth root looks like? A lot like root x. Okay, for 16, there's no issues there. It's continuous. The fourth root of 16 is 2. Now, the tangent function. We know the tangent function does have areas of discontinuity, but at 3 pi over 4, it's okay, right? It's continuous. So we can take the limit of the tangent of x as x approaches 3 pi over 4, and the tangent of 3 pi over 4 is -1. Okay, here we have the limit of x squared plus 5x plus 4 as x approaches 2. So if I want, I can do direct substitution into this. I could do the limit of each term and then add those together. Either way, I'm going to come out with the same end result. Remember, I can do direct substitution because I know this is a parabola that does not have any discontinuity. So if I plug this in and calculate, I get 2 squared plus 2 times 5 plus 4, which gives me a total of 18. Right? 4 plus 10 plus 4. Now here, the limit as x approaches 2, I can also do direct substitution. Okay, we already know this is 18. So the limit of x plus 4 as x approaches 2, that's 6, which gives me 3, okay, from the quotient. Now, just to show you another option, since I recognize that x plus 4 is a factor of the numerator, I could reduce that common factor, right? This is x plus 4 times x plus 1. So I can reduce out that common factor and make this the limit as x approaches 2 of x plus 1, and do direct substitution that way and get the 3. So that's actually how we can do direct substitution, and this will be in the upcoming lesson. We'll focus on more methods of calculating limits. But I could do, instead of, this is that example from the beginning where we looked at the values. Let me see if I can find the right one. Nope, there it is. Okay. That was this problem here where we used the chart, right, and took a look at the graph. Now we can do the direct substitution. So this is a little preview to one of the methods we'll talk about. Now, your notation is very important. I'm going to stress that. As you're doing your work, it's a lot of writing, but we have to do it to make our notation proper, right? We want to continue writing the limit as x approaches 3 until the very end, to where we do the direct substitution. So as you simplify your work, you want to keep writing this notation. Okay, that's important. You want to have good notation for next year in your calculus class. So here, let's see, I can pull out the x squared, and that's from the first two terms, that's x minus 3. I can pull out a -2, and that gives me x minus 3. So my factorization is x squared minus 2 times x minus 3, and that's over x minus 3. So here I'm saying the limit of this rational function is equal to the limit as x approaches 3 of the factorization, which is equal to the limit of the simplification, which is x squared minus 2. Now I can do the direct substitution, right? Here I couldn't do it from the beginning because I'd get 0 in the denominator. But now I can do direct substitution and do 3 squared minus 2, which is 9 minus 2. Here's where I can drop the limit notation and write 9 minus 2 equal to 7. So all the way up to, as long as you still have a variable in your expression, think about it that way, you need this limit notation. Okay, once you get to where you do the substitution, then you can drop the limit notation. So the limit of x squared minus 2 as x approaches 3 is equal to 9 minus 2, which is equal to 7, which is exactly what we got from our table. Okay, so I hope you enjoyed this introduction to limits. This is probably one of the things you will start with next year in your calculus course. So it's a nice little preview for next year. It's kind of a nice way to end our year. I'm glad we got to this chapter so you were able to see this. So have fun with this section, and I hope to see you soon, maybe on Zoom. If not, I'll be talking to you soon with the next lesson on limits. All right? Enjoy the rest of your day.